Let's start off with number one. This is really basic stuff. Characterize a gas. What is a gas? It's a phase of substance that has low density and indefinite volume and indefinite shape. And so do we have any of those choices here? The first one, yeah, low density. Right. Low density fits. Well, you can't have both. Low density and high density. Closely packed particles. Should we expect closely packed particles in a gas? No. So no increase in volume when temperature is increased. Right? That flies in the face of Charles' law. Right? Increase the temperature, you're going to increase the volume as long as the other two factors are constant, right? Number of moles and pressure. No decrease in volume when pressure is increased. Well, that flies in the face of Boyle's law. Right? So this is the only one that's true out of that whole bunch. It's A. Let's go ahead and put 2 up here. All right, pressure is. How is pressure defined? Remember, pressure is force per unit area. It looks like D to me. Right? It can't be measured in newtons. Newtons is simply a force. That's not enough. Yeah, let's move on. What's the SI unit of pressure? SI unit of pressure. Remember that one? And it starts with a P too. Right? Pascal. The Pascal is the unit of pressure. And how is it defined in terms of, it's a derived unit. So how is it defined in terms of other SI units? 1 Pascal is equal to 1 Newton per square meter. Okay. Newton is a derived unit too, isn't it? Right. Remember how Newton is defined? Use Newton's second law of motion. Right? If this is mass is a kilogram, and acceleration is meters per second squared, then that's equal to 1 Newton. Okay, so if you plug that in here, then the second squared is going on the bottom and meters goes on the top, and it actually turns out to be a kilogram per meter per second squared. Okay, so that was probably a little more information than you wanted. The Pascal is the standard unit of the SI unit for pressure. All right, let me see. That's not in your way, but it's in my way. It's the pressure, okay. A glass column is filled with mercury. It's 5. And inverted in a pool of mercury. That sounds familiar. The mercury column stabilizes at a height of 729 millimeters above the pool of mercury. That's a lot of wording to just say, you just built yourself a barometer. And all this is mercury. And this mercury, once you take your thumb off, goes down to 729. Difference between that, 729 millimeters. Sometimes I find it useful to draw pictures that clarifies things. What's the pressure of the atmosphere? And when you look at your answers, the answers are in atmospheres. Like This is the pressure, atmospheric pressure in millimeters of mercury. So what we're asked to do is unit conversion. We want to convert these units, 729 millimeters of mercury, into atmospheres. So that means we need millimeters of mercury down here to cancel and then leave us with atmospheres up here. So what's the relationship between atmospheres and millimeters of mercury? Remember that one? It's in useful information if you need to look it up. One atmosphere is 760. And so we divide 760 into that. And it's obviously not going to be A because that's greater than 1. And this divided by that has to be less than 1. So, and it can't be D, 456 atmospheres. So actually it's either B or E. Excuse me. It's either B, C, or E. So we just need to actually crunch the numbers. 959, 0.959 atmospheres. But 3 significant figures. Okay, we're starting off simple. Right. How about 6? The local weather forecaster reports that the current barometric pressure is 30.4 inches of mercury. What's the pressure in atmospheres? 30.4 inches of mercury. This is going to need another conversion factor in order to leave us with atmospheres, correct? So we obviously need inches of mercury down here, atmospheres up here. So what's the relationship? Do you remember that one? No, you do? What's the value? How many inches of mercury in 1 atmosphere? It's in your useful information. 2992. Yep. Okay, so we divide that into 30.4. And since this is the conversion factor, the significant figures here don't matter. This is the only one that matters right here. 3 significant figures. And 3 significant figures rounded off is 1.02. Okay. Okay. 8, and can I squeeze 9 in there? That's kind of difficult. Let's just stick with 8. That's not everything I handed out. That's all I have left. Okay, the air pressure in the inner tube of a tire on a typical racing bike is held at pressure of about 112 psi. Convert that to atmospheres. 112 psi. That's pretty high. I think my bike, when I was riding a bike, it was like 85 psi. 112 is pretty high. Those guys are like, the tires are like that. To reduce resistance, right? The higher the pressure, the less tire is touching the ground. So it doesn't slow you down as much. Okay, we want to convert that to atmospheres. Okay, so we need PSI to atmospheres. Remember what the conversion is there? 14.69 pounds per square inch equals 1 atmosphere. Right. So we have 112 divided by 14.69 is 7.624. Let's see, we've got 3 significant figures, so we have to round it down. 4 is less than 5, so 7.62 atmospheres. That would be B. Okay. All right. 9. Boyle's Law states. Let's see. Boyle's Law. What is Boyle's Law? Remember, in mathematical terms, pressure times volume is a constant. So whenever pressure goes up, volume goes down. It's an inverse relationship. Let's see. Equal amounts of gas occupy the same volume as constants. No, that's not Boyle's. The volume of a fixed amount of gas is inversely proportional to the pressure at constant temperature. So fixed amount of gas means number of moles is constant and the temperature is constant. That has to be, right? These 4 factors, if you let 2 of them vary, the other 2 have to be constant. So B looks like the best answer, doesn't it? Yep. Let's see, I'm pretty sure 10 is coming up. Yeah. Avogadro's law. Which one is Avogadro's law? It relates what? Volume and moles. And in that case, temperature and pressure must be constant. So let's see which one fits that. Equal amounts of gases occupy the same volume at constant temperature and pressure. Constant temperature and pressure. Okay. That works too. This says that that's constant. But another way of putting it is A. In fact, I think A is a better way. I mean, this is consistent with the other gas laws. Something times something or something divided by something equals a constant. But the more useful way is to say if these volumes are equal, right, the temperatures are equal, and the pressures are equal, and the moles must be equal. And all that says is we didn't change the volume any. Like for this one, we didn't change the volume any, so both that one, if we don't change the volume, then these have to be equal. That's another way of putting it. But if you do change the number of moles, then the volume responds. You know, direct proportion. All right. Let's see. Oh, we're going to get all the laws together first, huh? Charles' law. So which 2 factors are allowed to vary with Charles' law? Temperature and volume. So that means pressure and moles must be constant. So if we increase the temperature, we increase the volume. This is a direct proportion. So which one fits? The volume of a fixed amount of gas is directly proportional to its temperature in Kelvin at constant pressure. Fixed amount, constant pressure. Let the temperature vary, the volume varies directly proportional, right? And this has to be in K in order for that formula to work. All right, let's see. 15. Gaseous chlorine is held in 2 separate containers at identical temperature and pressure. The volume of container 1 is this, and it contains this many moles of gas. The volume of 2 is this. How many moles of gas in container 2? All right. Remember, under ideal conditions, a gas is a gas is a gas. Right? Doesn't matter what it is. So naming it as a chlorine gas with these parameters doesn't matter. They could be anything. Okay. Flashed a message. I had to check my power. Okay. So what type of situation do we have here? Is this a before and after or a state function? How do you know? We've got volume, and then we've got volume again. And we only have moles one time. That's a before and after situation. The relationship of volume and moles is whose law? Avogadro. So it's helpful to write these things down here and determine what their values are. So this is before, V1 is before. The volume of container 1 is 1.3. Now, I say before and after, but since gases are gases, doesn't matter what they are, then you can either do something to the gas or you can compare two containers of a gas. And it works the same way as before and after, in quotes. Number 1 is 1.3 liters. And how many moles does it contain? 6.70. 6.70 moles. Okay. Volume of the second container is 2.33 liters. And the moles in the second container is the question. So now that we know which one's which, we can plug them in the formula, or we can solve for this one. Let's go ahead and solve for N2. All right, bring it over here, and then flip this one over here as N1, V2, and then V1. Is that algebraically correct? Okay. So now we can just plug in the values. 6.70, I'm going to leave out the units just for convenience. V2 is 2.33, and V1 is 1.30. Right. So the number of moles in the second container should be the mathematical equivalent of that expression. 2.33 times and 1.3 divided. I get 12. Let's see, three significant figures, 12.0 liters. No, moles. Right, first time. Okay, so A is the answer to this one. All right, 15. Moving along. Let's see, where are we? That's 800 torr. Now we need volume, 1.72 liters. That's correct. 1.72 liters. And R is 0.08206 liter atmospheres per mole K. And temperature is 27 plus 273. Okay. So we can calculate the moles using this. We'll get moles of oxygen. Yeah. How many oxygen molecules? So we need moles first. Now we could incorporate conversion to molecules right here in this formula, but I think that would be a little confusing. So let's calculate moles first. So 800 divided by 760, and then times 1.72, and then divided by 0.08206, and then divided by, what's that, 2090, 300, right? 27 plus 273. Okay, so I get okay. That's moles of oxygen. Now we can convert that to molecules. So moles, 1 mole is equal to what? How many molecules? Everybody knows that one. Avogadro's number, right? Okay. Let's see if you get the same thing I do. 6.022 exponent 23. Rounded out to 3 significant figures. Anybody got an answer? Or are you waiting on me? 4.43 times 10 to the 22nd molecules. That would be A. It was 30. 37. All right, which condition of pressure, temperature, and moles respectively are most ideal? Remember that one? Gas, what they mean is, under what conditions does every gas behave as if it was an ideal gas? Pressure, temperature, and moles. Okay, in that order: pressure, temperature, and moles. Pressure, low pressure. Temperature, high temperature. Moles, low moles. All right, so that would be E. Low, high, low. And you'll get a gas that behaves ideally. What do we mean by ideal behavior? Don't remember. Maybe we'll get another question on that one. So I'm gonna steal my own thunder. Let's see. I think I've got. Not here yet. All right. Who's next? 30. We did 37. Scroll 40. .1 gram sample of neon gas exerts a certain pressure in a container of fixed volume. Okay. What mass of argon is required to exert half the pressure at the same conditions of volume and temperature? All right, so we got 40, we're given 41.1 grams of neon. Okay. and it's in a container of fixed volume. Volume is constant. Okay. Certain pressure. Okay. And there's a pressure associated with the neon. Right? So it has an exact value. So when the neon is in here, it gives you this pressure. What we want is what mass of argon is required to give you half the pressure. So here we go again. Neon is 20. Argon is about 40. So how much argon would be required? Right? How many particles of argon would be required to give you the same pressure? Right? Twice as many particles, right? Well, to give you the same pressure, the same number of particles, which would be twice the mass. Okay, so if we had the same number of particles, it would be twice the mass would give you the same pressure because it'd be the same number of particles. But we want half the pressure. So if this pressure, exactly, if we want half the pressure to be the pressure of argon, and pressure and moles go hand in hand. As long as you keep the volume constant, temperature constant, then the pressure is directly proportional to the number of moles. All right. So if we want something, if we want half the pressure under these conditions, then we would need half the moles. Excuse me. We would need the number of moles of neon to be cut in half would be the number of moles of argon, correct? Does that make sense so far? Okay. To get half the pressure, we need half the moles. So half the moles of neon, yeah, half the moles of neon would be half the mass that we have, wouldn't it? This would give us a certain number of moles of neon, but we only need half of those. Now that would be, that, wait a minute, that would be the mass of neon. Okay, I got a better idea. Let's convert these to moles of neon. So it'd be about 20.2 grams per mole. So how many moles of neon would that be? 41.1 divided by 20.2 is 2.035. 2.035 moles of neon. Okay. With half the pressure, we would only need half the number of moles, right? So half the number of moles here would be equal to 1.017 moles of neon would give you half the pressure, but that would be the same number of moles of argon, right? If we got half the pressure, we need half the moles, but up to this point, it doesn't matter what gas it is. Okay, so the same number of moles of argon as neon would give you half the pressure that it has now. Now we convert this back into mass to see what the mass would be. Grams per mole. And argon would be 39.95. And that would be equal to 40.6 grams of argon. Will give you half the pressure of the neon. Well, rounding error, 40.7. Okay. I think this follows a more logical trend. Since we actually have a real number to deal with, and then that's a better approach than trying to do it algebraically, mathematically. You can get lost in the unknowns. Does anybody have questions about that? No? Okay. Yeah, I'm paranoid. I keep watching to see him. I'm still visible. Okay. Let's see. We'll skip a few. Oh, okay. For which gas are the molecules diatomic? Is this part of this lesson? Oh, 4 identical 46 through 51. Okay. So we need these conditions. 4 identical 1-liter flasks contain gases helium, chlorine, methane, and ammonia, each at 0 degrees and 1 atmosphere pressure. All right. 0 degrees for gases. When we're talking about gases and nothing else, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere pressure. That's standard conditions for gases when we're doing these gas problems. Later, when we're doing other types of problems, stoichiometry, if it says standard temperature and pressure, standard temperature there is 25 degrees in 1 atmosphere. All right, so we got these flasks with helium, chlorine, methane, and ammonia. Okay, 1-liter flask, 1 liter of each. Okay. At 1 atmosphere pressure. And 1 atmosphere. Okay. Now let's go down to 49. Question is, which of these molecules are diatomic? We didn't need to know all that stuff. That's the only diatomic molecule in there. Let's see, is that that's the only one I picked out of those? Which gas has the greatest number of molecules? Let's do that one. 48. Greatest number of molecules. Well, if they have, assuming the temperature is the same also, if they have this volume at this pressure, they're all the same pressure, which one has the most molecules? The lightest one. Right, the lightest one. Oh, excuse me. No, if they're the same temperature, pressure, no, they all have the same number of molecules. Hopefully. Let's see. What was I going to do? Oh, 47. Yeah, I wanted to look at 47 also. Right. So for which gas do the molecules have the highest average velocity? For that one, since they're all at the same temperature, the highest velocity is going to be the lightest one, because temperature is a measure of the average kinetic energy. And if one gas has the same kinetic energy as the next, the one's molecules that are going the fastest, because kinetic energy is equal to 1/2 mv squared, that if they have the same kinetic energy, if each molecule weighs less, if its mass goes down, velocity has to go up. So the lightest one is going to be the fastest one, right? Would that be helium? Yeah, that'd be helium. It's the lightest one out of that bunch. Which gas has the highest density? Well, the highest density, since they're the same number of particles in all of it, then the heaviest one is, they're going to occupy the same volume. So remember, density is, well, this is 46. Highest density is mass per unit volume. volume's the same for every one of them. So the one that has the highest density is going to be the heaviest one. Right? So we need to look at, let's see, this is about 70, 35, 45. This one is about 12 and 4 is 16. And this one's 14 and it's about 17. This one's 4. Right? So that one, chlorine would have to be it. Chlorine would be the heaviest one, therefore it'd be the densest one. All right. For which gas are the collisions elastic? What do we mean by elastic collisions? Anybody have physical science or physics? Right. There's right in scientific terms, there's no loss of kinetic energy in a collision. If there's a loss of kinetic energy, that's an inelastic collision, and that can vary from 99 down to 0. Right. So, by the way, if it's an inelastic collision and you lose kinetic energy, where's the kinetic energy go? Usually it turns into heat, right? Like what we call friction, internal friction, or whatever the case may be. So which gas molecules have the smallest average kinetic energy? Well, they all have the same, right? Because temperature, if they're at the same temperature, temperature is a measure of the average kinetic energy. If they're all at the same temperature, they all have the same kinetic energy on average. Inelastic?
Or why is it called elastic and inelastic?
Those are terms that refer to bouncing off each other.
Oh, okay.
Yeah.
I didn't know if it was something different or if it was like this.
Oh no, that's right. Right. That's a empirical description. If you're playing pool, the balls that smack each other, those are completely elastic collisions. Right. So that's why when you're the one that gets to break, you smack them as hard as you can. Right. Send them everywhere. Because it's easier to sink balls that are separated from each other than the ones that are bunched together. Because you can calculate their geometry, their trajectories easier when they're separated. So you want to smack them hard the first time. And sometimes you can get 2 or 3 of them in the pockets that way. All right. How we doing? We're gonna run out of time. And I thought I was doing pretty good. Yeah. Well, this is a short lab. We can spill over a little bit. Everybody knows it's a short lab, don't you? Right, because you've already prepared your notebooks and you've read the procedure and you know. Okay, yeah. Let's see. Why is okay, 52. The mass of 1.12 liters of gas, Y, at standard temperature and pressure is found to be 6.23 grams. The density of Y is what? Okay. We're given gas Y has a mass, a volume, excuse me. Volume equals 1.12 liters. And it's found to be 6.23 grams. 6.23 grams. Okay. Oh, this is easier than it looks. Density. They're just asking for the density at standard temperature and pressure. It doesn't matter. Standard temperature and pressure is fine, but we've got the information we need, right? Density equals mass per unit volume. So you should divide this mass by that volume and see if those units, grams per liter. Yep, that's one of the answers. So if you divide this by that, you should get around 6 high 5s or low 6s. Right. So looks like the closest one of that would be B. Right. Without even calculating it. Okay. It's simple calculation. 53. Oh, it's the same gas. The molar mass of gas Y is, oh, this is going to take a little more doing. So we've got the same gas Y. We've got a mass of 1.12 liters, excuse me, a volume of 1.12 liters. Standard temperature equals 0 degrees C, and standard pressure is 1 atmosphere. Okay. And the mass is 6.23 grams. So what do we calculate molar mass? Molar mass is mass per moles. We got mass already right here. What we need is moles. Can we get moles out of this? Yeah. PV equals nRT. Number of moles equals PV divided by RT. We have pressure, we have volume, we have temperature. And they're in the correct units. So what we have to do is just plug them in. Right? 1 atmosphere, volume 1.12 liters, 0.08206 for the R, and temperature is 273 K. Right. So, oops, didn't break. 1.12 enter 0.08206 divide, and 273 divide is 4.999 times 10 to the minus 2 moles. So molecular weight would be grams, 6.23 grams, divided by 4.9. That's 2 moles. And I get 3 significant figures. Yep. 125 grams per mole. That would be C. Okay. That one took a little more doing. Let me see. What's next? Oh, 54. Deliberately left blank. I think when I was working with the question banks to build this review document, the authors had incorporated a question, which turned out to be number 54 in my list, that we didn't have enough background to answer it. I don't know how it made it in there, but it did. So I'd already made up the thing, and I'd already done the handwritten description. So I just threw it out. Otherwise, I'd have to go back and renumber every one. All right, so let's see. Density at, okay, I'm trying to read that one. Argon. 5. Argon has a density of 1.78 grams per liter. 1.78 grams per liter at standard temperature and pressure. 1 atmosphere. Okay. How many of the following gases have a density at SDP greater than that of argon? All right. Well, let's go back to that comparison. If we have argon and it's about 40, yeah, about 40 for each, 40 atomic mass units for each atom. Then how about for this one? That'd be 3545 times 2. Right? So what's that? That's 90, isn't it? Or 0.9. And this is 74 grams per mole. How about the next one? Helium. Helium is 4. Ammonia. It's 14.01 for nitrogen and 3.03 for all of the hydrogens. right? 3 times 1.01, which is 17.04 grams per mole. And the last one, NO2. Right? Yeah, NO2. So this one is again 14.01 for the nitrogen plus 2 times oxygen, which is 2 times 16, 32. And that would be 46.01 grams per mole. So this is going to be 40 grams per mole. This one's going to be 4 grams per mole. All right, so back to the question. How many of the following gases have higher density? Well, at standard temperature and pressure, and the volume is 1 liter, right, per liter. So liters, pressure, volume, pressure, and temperature are all the same. That means we're counting on the same number of particles. So the more dense one is going to be the one that has a higher molar mass than this one, right? Which would be this one and this one. So 2 of them are more dense than argon. Did I do that one too fast? Are we good? What we did was we took the, since density is grams per liter, and we're at standard temperature and pressure, which means the volumes are going to be the same. Right? So we just take this one out of the equation. They're all the same volume. So we really only have to focus on that one. What's the mass of each one? That's why we're comparing just the masses. Because the liters, temperature and pressure are the same, and volume is going to be the same for density because it's an intensive property. It doesn't matter how much you have. Each one of them, each atom or a mole of each atom is all the comparison we need to tell which one has a higher density. Okay, 56. All right. Which of the following is the best qualitative graph of pressure versus molar mass? Oops, I'm covered up here. So 1 gram sample of different gases at constant volume and temperature. Pressure versus molar mass. What we need is a relationship between molecular weight and pressure. And what formulas do we have available to us? Well, molecular weight or molar mass is mass per unit mole. We also have our ideal gas equation. And we have, what's the other one? Oh, we only have 2. Yeah, we only have 2. Just these 2. So here's our pressure and here's our molecular weight. Let's put them into a single. If we solve this one for moles, then that's mass over molecular weight. And this one can go right in here like that. Okay, so PV equals MRT over molecular weight. Okay, let's bring molecular weight over here because these are 2 variables. Molecular weight, let's put mass RT over volume. Mass is, this is constant, standard temperature, and constant volume, right? So all of these are equal to K, correct? Now it's making sense to me. We let these 2 vary, but under the conditions we selected, these are all a constant. So what does that look like? That looks like the same shape as Boyle's Law, right? As this one goes up, that one goes down. So we should have a graph like that. and we don't have it. That's why none of these is the answer. The only way to solve this one is mathematically. Right. If I tried to be logical, but it didn't work. All right. Well, we're already over. How many more do I have? Okay, let's read from there. 58. Given this reaction, you react 5 liters of ammonia, 5 liters of chlorine measured at the same conditions in a closed container. Calculate the ratio of pressures in the container. Final pressure, initial pressure. Okay, let's put this on the board. It's not jumping right out at me. This is a gas, 3 chlorines yields 1 nitrogen gas and 6 hydrogen chloride gas. Okay, we're starting off at 5 liters of ammonia, 5 liters of chlorine. Here's the stoichiometry of the reaction, the balanced equation. 2 ammonia gas, 3 moles of chlorine gas yields 1 mole of nitrogen and 6 moles of hydrogen chloride. We're also given that at the beginning, we have 5 liters of ammonia and 5 liters of chlorine before the reaction starts. And the initial conditions are all the same. So what we can do is set those conditions wherever we want. It doesn't matter really, because we're looking for, the question is, what's the final pressure divided by the initial pressure? What's that ratio? So in fact, what we're looking for is the ratio of the final number of moles to the initial number of moles. Okay. Now, one way we can do this, and in fact, the worked problems has both ways incorporated. The quickest way is to just use X for values, X for this amount, and then go from there. But what I'm going to show you now is an alternate method where you actually use real numbers. And in order to use real numbers, we have to make an assumption. Let's just assume that the conditions, the same conditions that they're discussing here, are standard temperature and pressure. So standard temperature is 0 degrees C. 0 degrees C, which would be plus 273, would be 273 K. And beginning pressure, initial pressure, is 1 atmosphere. Yes, 1 atmosphere. Initial pressure is 1 atmosphere. So we've already got the value here, right, for 1 atmosphere. Under these conditions, we're going to calculate the final number of moles. Actually, we're not going to calculate the final pressure unless we want to. What we need to do is what's the final number of moles divided by the initial number of moles. But these are initial conditions. Now, if we use these initial conditions and we want to find out how many moles does this represent for each one of those reactants, then we would use this equation, right? PV equals nRT. The number of moles would then be PV divided by RT, right? For the initial, let's see, the number of moles, well, actually, since we've got 5 liters of ammonia and 5 liters of chlorine, the number of moles of each will be exactly the same. Right? Because the gas laws don't care what the gas is. So if we calculate the initial moles for this one, we got it for that one also. So 5 liters would be initial pressure of 1 atmosphere, and the volume is 5 liters, and R is 0.08206, and temperature is 273. Okay. So quick calculation. Five divided by 0.08206 and divided by 273 is 0.2232 moles. So that means under the conditions that we have chosen, and because the problem said they're under the same conditions of temperature and pressure, and the volume's a constant, right? It's going to be 5 liters of this and 5 liters of that. Then we can pick our conditions. And when we pick our conditions, then we come up with 0.2232 moles here and 0.2232 moles here. Okay. Now, how do we tell which one's limiting? Well, we need, if this represents 3 moles of chlorine, out of that 3, we only need 2 to make, so this one would be limiting, this will be excess. But let's find out, let's see. We're going to have to find out how many moles are over here anyway, right? Because we need to know the final number of moles, right? Which is proportional to pressure. So let's just go ahead and calculate. This one would be chlorine, and we're going to find out nitrogen first. That would be going downhill. Let's try this one. So this would be the chlorine. Chlorine, nitrogen, that's 1, this is 3. Right? So 1/3 of 2232. Let's see. Is 0.074744. Yeah, this is moles of nitrogen. Okay. If we use this one, just to check ourselves, to be sure, we're saying that this one is the limiting one. It makes this excess. Let's just be sure, right? So 0.2232 ammonia, if we convert that to nitrogen, then it's 1 nitrogen and 2 ammonia. So that would be half of that, 0.1116 moles of nitrogen. Right. So we know that this one is limiting, this is excess. Okay. All right, so we don't need to keep that because this one's not going to be used for the nitrogen anyway. What we need to do is find out how much of this one has been used. This is completely exhausted. Chloride is gone in the final amount. So initial would be this much. And final would be 0 for that. So let's find out how much of this is used, right? What we have to do is convert this into that. 0.2232 moles of chlorine and find out how much of the ammonia has been used. So we have 3 here and 2 there. So 2/3 of that represents the amount of ammonia that's been used. Okay. So let me swap this one and times 2 divided by 3. So this is going to be 0.1488 moles of ammonia consumed. Okay, it's used up. In the final amount, that much ammonia is gone. How much is left over? Well, what's left over is 0.1488 subtracted from this. Right? So I get 0.0744. That's what's left over. Remain. Okay. So this many moles remain. This many moles were created. Right. So we've got this in the final mixture, that in the final mixture. How much of this in the final mixture? Well, the ratio here is 1 to 6, right? So for every one of these, you have 6 of those. And I get 0.4464 moles of HCl. Right? So we've got this, those two, plus this left over is what we have in the final mixture. That's it. That's the final moles. So we add them together. 0.0744. This is ammonia. And 0.0744. This is nitrogen. And 0.4464 HCl. Let's just add those together. Let's see, 0.0744 plus. So I get 0.5952 moles equals final. This is the final moles. The beginning, the initial moles was 0.2232 and 0.2232. So the initial moles equals 0.2232 plus 0.2232, which is equal to 4464 moles initial. So, and we know that the ratio of pressure is equal to the ratio of moles of total gas. So now what we need to do is say this final pressure divided by initial pressure is equal to final moles divided by initial moles, which is equal to final moles 0.5952 divided by 0.4464. Let's see. There we go. And this is 1.33. That's the ratio of the final pressure to the initial pressure. Wherever we started. Now we chose 1 atmosphere, right? If you actually start at 1 atmosphere, then the final pressure will be 1.33 atmospheres. But we just use that assumption in order to make these calculations. If the pressure is actually 2 atmospheres, the calculations would still work because we're talking about a ratio, not absolute. So the ratio then, 1.33, just multiply by 2, and the final pressure would be 2.67 or 2.66. Okay? Right. So that agrees with the key, which is good. All right. Number 61. this method required more math. The other method where you use only x's required more algebra. Okay, let's go on to 61. All right. 61. 0.72 grams of a liquid is vaporized at 110 degrees Celsius and 0.967 atmospheres. The gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Excuse me. All right. Let's put down what we know. This is an exercise in the Dumas method. All right, so this gives you a head start against next semester when we actually do this one in the lab. 0.72 grams. Mass equals 0.7, whoops. Yeah, 72 grams. Right? So if we're looking for the molar mass, which is what we need, right? If the empirical formula is CH2, what we want is the multiplier. And whatever that value is, times those molar masses for the individual atoms, whatever that value is, will give us the molar mass that we're going to calculate. Okay, so we've got the mass, we need the moles. And we're going to get the moles using the gas law. So the temperature is 110 degrees Celsius, which would be, let's see, 383 degrees. No, sorry. We don't do that. Just K. How about pressure? 0.967 pressure. 0.967 atmospheres. Okay. And it occupies a volume of 559. Well, volume equals 0.599 liters. That's what we should have. Why do we need liters, atmospheres, and K? Because the gas constant is in liter atmospheres per mole K. So these are the correct values, the correct units of measure for each one. Okay, now we need to calculate the moles so that we can calculate the molecular weight or the molar mass. And so PV equals nRT, and N equals PV divided by RT. So the pressure is 0.967 atmospheres. Volume is 0.599 liters. R, 0.08206 liter atmospheres per mole. Okay. And temperature, 383 K. So that calculation will give us the number of moles. And 0.08206 divided 3 divided. This is 1.843 times 10 to the minus 2 moles. Okay, molar mass. The true molecular weight or the molar mass of the compound is grams per mole. 0.72 grams, 1.843 times 10 to the minus 2 moles. 0.72 is 39.7 grams per mole. Okay, that's the true molar mass. What is the empirical mass, or the empirical weight? Well, it's 12.01, right, for carbon, and then 2.02 for 2 hydrogens, which is what? 24.03 grams per mole of that weight. So what do? Well, we need 39.7 divided by 24.03. Which is 0.62. That's not a whole number. All right, so what do we do with that? Well, let's see if I did it right. Pause for a moment. Let's be sure I did my math correctly. 383. That's correct. 0.967. Yep. 0.599. Yep. 0.08206. Okay. So this is, yep. So let me do that calculation once more. 0.08206 and 383 divide 10 minus 2. Okay. 0.72. 39.1. Right. How about this one? CH2, 12.01. Is that correct? Yeah, CH2. 12.01 and 2.02. All right. So that's wrong. There it is. 14.03. There we go. Now, that's 2.78. All right. We're going to have to take some real liberties here. That's not real close to 3, but it's closer to 3 than it is to 2. So if we assume that an experimental error, and this is equal to 3, then it's C3H6. Now there's another way to do this also that's explained in the my handwritten work problems. In order to do that one, we take this formula, and we also take molecular weight equals mass divided by moles, and we convert this to moles equals mass divided by molecular weight, and then we substitute that in here, right? So PV equals mass divided by molecular weight times RT, and then we solve for molecular weight. So that brings it over here to MRT over PV. And then we substitute the values that we have, MRT, P, and V, and that gives us the molecular weight in one calculation. And that should come out to something in this neighborhood. Actually, it comes out to something bigger than that. 41.86. I think what we have here is rounding error. So if you do it that way, let's see if we have mass RT. Let's just do that. Molecular weight equals mass 0.72 grams, 0.08206, temperature 383 K divided by pressure 0.967 atmospheres, and volume 0.599. So let's see what that gives. 0.72 enter, 0.08206 times 383 times 967 divide, and 0.599 divide. And that gives us 39. That gives us the same as this one. How did I come up with that answer before? Okay. Well, This is going to come up with, with the same answers before, 39.1. So we're still going to have to round and take into account a significant experimental error. That's number 61. Okay. Next. Oh, we skipped quite a few. Number 80. Okay. Okay. If M is the molar mass, what I usually write is MW. M is the molar mass, R is the gas constant, T is the temperature, P is the pressure. Which of the following expressions represents the density of a gas? Okay, so we've got to deal with density equals mass per unit volume. We've got to have a formula that gives us molar mass, which is mass per unit mole. And then we've got pressure, temperature, R, and so forth, volume. So we got PV equals nRT. So we want to combine those three and solve for density. Solve for this one. So the way I would do it is I'd combine these two first. Right? This is N, solve for moles. Moles equals M over big M. Molecular weight. And then substitute this one in here. So PV equals little m over big M times RT. Okay. Now, if we want to solve for density, we need to make a substitution here. Right? So we could either solve for mass or we could solve for volume. It should work either way. So let's solve for volume. Volume equals mass divided by density. So that would be P times mass over density, right? That V equals this V. So it's that amount we're going to substitute right there. This is MRT over big M. Okay, so now we want to solve for density. If we move density over here and move everything over here, that means when it comes across, it flips. So we have P, M, and then it flips to M, R, T. Oops. This is little m, and that's big M. Right? So we bring big M over here with that little m, P, M, big M. And then this one goes over here, density. Then that little m goes over here, R and T goes over here. So the little m cancels. And we're left with density equals P divided by molar mass over gas constant times temperature. So let's see which one that is. P big M over RT is A. Right? That's how we solve that one. Got to know a little algebra. All right, who's next? 81. Okay. That works because this one is writing better than my black ones. One way to isolate metals from their ores is to react the metal oxide with carbon as shown in the following. Okay, so 2 MO, and that ratio I assume is fixed. 1 mole of M, 1 mole of oxygen, or 1 atom of M and 1 atom of oxygen in the solid, plus carbon yields the free metal, M, plus carbon dioxide. So if 34.08 grams of metal oxide react with excess carbon and 4.37 liters of carbon dioxide formed at 100 degrees and at 1.5 atmospheres, what's the identity of the metal? All right. So we have 2MO solid plus carbon solid yields 2 M's plus carbon dioxide. Correct? Yes. Okay. Let's work backwards from the question. What's the identity of the metal? How do you identify an element? Well, it's only 2 ways that I know of. One is if you have the atomic number, the Z number, the number of protons. I don't see how we can get it from this. But another way is to calculate its molar mass. If you know the molar mass, then you can get really, really close in the periodic table. So that's where we're headed. We're going to do the molar mass, molecular weight equals mass divided by moles. Okay? We have 34.08 grams of metal oxide. So we do know this mass, 34.08 grams of metal oxide. And with excess carbon. So this is not limiting. We're going to consume all of that. And we're going to produce what? We're going to produce 4.37 liters of carbon dioxide. All right. And at 100 degrees Celsius and 1.5 atmospheres. All right. So I think that we can calculate the number of moles of carbon dioxide. Yeah. Because we have volume, temperature, pressure. And in our ideal gas equation, the only other variable is moles. So we can solve for that one. Right? PV equals nRT, solve for moles. Why do I want to do that? Well, if I know how many moles of carbon dioxide are produced, I can calculate how many moles of metal are produced. Okay? That's one step. That gets this part right here. We still have to calculate the mass, but we can get the moles from the gas equation. So this is PV over RT. Okay? So pressure is 1.50 atmospheres. And volume is 4.37 liters. R, of course, is a constant, 8206. And temperature is 100 plus 273. Okay? So we can calculate the number of moles of carbon dioxide. 1.5, 4.73 divided by 0.08. 206 and divided by 373 K. All right. So that's, see if this one writes any better. That's 0.2318 moles of carbon dioxide. Now we want to know how many moles of metal. Well, for every 1 carbon dioxide, you get 2 metals. So times 2 is 0.4636 moles of M. Let's try this. We do know how many moles of we know how many moles of the metal are produced, and it's 2 to 2. So that's exactly the same number of moles of metal oxide. 0.4636 moles of metal oxide. You know, we can calculate the molar mass of that compound. You know, we may not need that formula. Let's calculate the molar mass of MO. Right? Molecular weight of MO equals 34.08 grams per 0.4636 moles. What about that? 34.08. So this is 73.5 grams per mole. All right. How do we find the molar mass of a compound when we know the formula? We add up the molar masses of the individual parts, don't we? So we know that the molar mass of oxygen is 16. So if we subtract 16 from that, is that 5? All right, 6 and 13, 1, 6, 5. This is the molar mass of M. Right? Because that's the oxygen we removed from it. This was the total for the whole compound. We removed the oxygen, and that's what's left over, 57.5. Okay, now, how do we identify the metal? Well, we look at the periodic table, 57.5, and find the nearest one to that one. All right, I think I made a mistake here. Let's do this calculation one more time. $1.5 times 4.37, 1.5, 4.37 times divided by R. Yeah, 0.08206. And then divided by 100 plus 273, right? 100 plus 273, 373. I did make a mistake. This is 2.142. So 2 times that. Actually, we don't even need to know this. Right, 2.142 is moles of carbon dioxide. One of these for every 2 of those. Well, we do need to know 2 of those. 4283. So this one is 4283. Or 283 because it's 2 to 2, and that's 2, right? So it's going to be that much. And 283, so 34.08 and 0.4283 divided is 79.6. So this is going to be 6. It's going to be 3. This is 63. Okay, so the molar mass of our metal is 63.6. That's copper. There we go. All right. 81, 82. Oh, this one's simple. Let's clear the board. $82. The standard temperature for gases, I've already told you that one. It's 0 degrees C. 83, standard pressure for gases, 1 atmosphere. There you go. That's just memory. All right. This one is 86. (142 milliliter sample of gas is collected over water at 22 degrees C, 750 torr, 753 torr. What's the volume of the dry gas at standard temperature and pressure? The vapor pressure of water at 22 degrees is 20 torr. All right. Let me draw you a picture. We're collecting a gas sample over water. All right. I don't think we got a chance to discuss this in the lecture. So let me draw you a complete picture. What you would do is have, right, your water here. You would also have an inverted graduated cylinder. There we go. So we got volume marks on it. Okay, and it's full of water all the way to the top. Right? It's like our barometer. You fill it up, then you clamp your hand over it, and then submerge it in water. And then to collect the gas, we have a reaction vessel over here. And what happens is the gas collects here and it displaces that water. The gas goes like that, displaces the water. Okay, what are we told? Well, the temperature here, T equals 22 degrees C. And the pressure, the vapor pressure here, pressure on the water is 753 torr. Okay. We want to know the volume of the dry gas. And we also know the vapor pressure of water. So what's going up here is a combination of the gas, the total pressure equals the pressure of the atmosphere plus the pressure of the gas. We want to know this one right here. So total pressure is 753 torr. Pressure of the atmosphere. Just a second. Let's see. Volume gas at STP is collected over water. 753 torr. Yeah, that's the total. That's the total pressure, and this is the pressure. Actually, it's the pressure of the gas plus the pressure of water vapor. That was my mistake. Water vapor. So up here you have gas, water vapor plus gas in that space. Okay. So if this is the total pressure, and we were given the vapor pressure of water at that temperature is 20 torr. So we're given 20 torr here, plus the pressure of the gas. Then the pressure of the gas equals 753 minus 20 equals 733 torr. Okay. So that's 733 torr for the dry gas. But we want to know what's the volume of the gas under standard temperature and pressure. So now that we have the dry gas value here, then we need to say, all right, if we know the before condition of 733 torr for the gas, we want to know standard. Let's see, this is before, pressure before 733 torr. Okay, the volume before is 142 milliliters. Pressure, volume, and the temperature before is 22 degrees C plus 273, of course, equals 295. Okay. Okay. Now, under what conditions do we want to report? We want standard temperature and pressure. So standard pressure, the conversion is going to be to this one. The standard pressure is 1 atmosphere or 760 torr. We don't know what the volume is. That's the question. The temperature is going to be 0 degrees Celsius, which is 273 K. Now we have the data, and that can tell us which formula we need to use, right? P1 V1 over T1 equals P2 V2 over T2. So we're going to solve for V2. V2, P1 V1 T2 divided by T1, and we're keeping V2 over here, divided by P2. So P1 is 733 torr. V1 is 142 milliliters. T2 is 273. Okay. T1 is 295. Okay. And P2 is 760 torr. So this should give us the final volume under conditions of standard temperature and pressure. 733, 142, 273, 295, 760. Oops, let's start over again. 733 times 142 times 273 divided by 295 and divided by 760 is 127. 127 milliliters. Oh, so the answer is E, none of these. This is the correct answer, but it's not up there. Right? One's real close, but not close enough because we have the option of none of these. That will give you the correct answer. All right. Next, 86, 88. Oxygen gas generated by the reaction. 2 potassium chlorate. 2 potassium chlorate decomposes into potassium chloride plus oxygen gas. Right? And we need 2 here and 3 there. Okay, that's the balanced equation. This oxygen gas, because oxygen gas is the only thing collected. It's collected over water at 27 degrees in a 1.55 liter vessel at a total pressure of 1 atmosphere. Okay, what they're saying is that the collection volume is 1.55 liters at a pressure of 1 atmosphere. The vapor pressure of water at 27 is 26 torr. Okay. How many moles of KClO3 were consumed in the reaction? All right, so what we need is how many moles of oxygen were produced. Then we can work our way back to this one. So with our model, and we have like that, and then we have like this, and like this, just like that. And we have the bubbles going up here, and it gives us a certain amount of volume. And our reaction vessel here is our potassium chlorate decomposing and giving off gas. This is oxygen. Okay. Now, what we're given is this is at 27 degrees. T equals 27 degrees C. Might as well do it. This would be 300. Okay. Okay. And pressure is 1 atmosphere. This is total pressure equals 1 atmosphere or 760 torr. So the pressure of the oxygen is 760 torr minus the contribution of water vapor, which is 26 torr. And so let's go ahead and calculate that. 760, 26 minus is 734. So that's the pressure of oxygen. Okay. Now, 1.55 liters is the volume. This is 1.55 liters right here. Okay. Now we have pressure, we have temperature, we have volume. We can find out how many moles of oxygen were produced. PV over RT. So pressure is 734 torr, but we need atmospheres. 734 divided by 760 is atmospheres. Volume is already in liters. That's good. R is 0.08206, and temperature is 300 K. Okay. So the number of moles of oxygen are, wait for it, 734 enter 760 divide. This is 0.9658. 0.9658. Atmospheres. Times 1.55 divided by 0.08206 and divided by 300. So this is 6.081 times 10 to the minus 2 moles of O2. How many moles of KCl3 were consumed? That will answer the question. So what we need is to convert this to KClO3. And the ratio is 2 of these for every 3 of those. And that's 4.05 times 10 to the minus 2 moles of KClO3. Oh, they've got it in standard notation, so we got to move 2 places to the left. 2.0405 moles of KClO3. That would be C. Okay. All right, that's 88. Next. Okay. This is a good one. Okay. 94. All right. 94. And what we have is two bulbs filled with gas at different pressures, and then we're going to open the valve and let them mix. What we want to determine is what's the final pressure after we open the valve. Okay, so let's draw our picture first. We've got a 3-liter connected with a valve to a 2-liter, right? 2-liter, a little bit smaller. All right. The gas pressure in the 2-liter is 1.8 atmospheres. Okay. And the 3-liter is at a pressure of 3 atmospheres. Okay. That's everything given. What we want is the final pressure. Okay. First of all, what do we know when we have two gases mixing? The final pressure is equal to the pressure of gas A plus gas B. So if we figure out what is the pressure going to be for this gas, what is the pressure going to be for this gas after we open the valve, then we can add them together. Right? So what we're looking for is the pressure of the 3-liter valve plus bulb plus the pressure of 2-liter bulb. All right? How are we going to do that? All right, because they're going to mix. Right? How do you get them separated? Well, here's the way you do it. You do it in your head. Assume that this is a vacuum. Assume there's nothing on this side. Then when you open the valve, this gas is going to rush in and equalize, and we have a before and after situation for that side. Then you go back and do the same thing with this one. Assume that one's a vacuum. Open the valve and let it produce a final pressure. So now we know the pressure of this one after the valve. We know the pressure of this one after the valve. Plug in the numbers and add them together. All right. So the first one here, if we assume that's a vacuum, then the first pressure is 3. The first volume is 3. The final pressure is unknown. What's the final volume? The final volume is 3 plus 2. So we have a before and after of Boyle's Law. We're going to combine Boyle's Law and Dalton's Law of partial pressures. Right? So what we're going to do here is say, all right, 3 times 3 is this one before equals P2 times 5. Right? So P2 is going to be equal to 3 times 3 is 9, 9/5. Right? 3 times 3 is 9 divided by 5. So what is that? Let's see, it's 1.8 atmospheres. Correct? Put it in your calculator and see if I'm right. Then we'll do the same thing on this side. Right? The first pressure is 1.80 atmospheres. The first volume is 2 liters. All right. The second pressure for this side is unknown. And the final volume is exactly the same. Right, because it's expanding from 2 into 3, which is a total of 5. So now we set this one up. These two times each other, 1.80 times 2 equals the second pressure times 5. Right? So this is what? 2 times 1.8 is 3.6, isn't it? 3.6 divided by 5 equals the second pressure. All right, so let's see what that is. I can't do that one in my head. Well, I guess I could, but it'd be a challenge. 0.72, 0.72 atmospheres. So the total equals 1.8 plus 0.72 equals, let's see, 2.52 atmospheres. Let's see, we gotta pull up our answers. Yeah. Okay. Takes care of 94. Right. 95 coming up. Partial pressures of methane, nitrogen, oxygen in a sample of gas were found to be 135 millimeters, 508, 571, respectively. Calculate the mole fraction of nitrogen. Okay. This is really, really simple. If we have the partial pressures are proportional to the number of moles. So if methane is at a pressure of 135 millimeters of mercury, and nitrogen is at a pressure of 508, and oxygen is at 571. Okay, what's the total? The total is 9, 14, carry the 1, 4, 11, carry the 1, 2, and it's 12. That's the total pressure in that container. Okay, the mole fraction, by definition, of which one? Nitrogen. Would be the moles of nitrogen divided by the total moles. That's also proportional to the pressure of nitrogen divided by the total pressure. So knowing that, we can take this 508 divided by 1214, and that will give us the mole fraction of nitrogen. Which is 0.4185. Or round it off to 3 places, right? 419. 0.419 is the mole fraction of nitrogen. Well, rounding error. C, 0.418. That was 95. All right, 96. Dalton's law of partial pressures. Okay, what does this state? Well, it states that the total pressure of a mixture of gas is the arithmetic summation of the partial pressures of each of the individual gases. So which statement comes close to that one? Which one mentions pressure total? D, total pressure of a mixture of gases is the sum of the partial pressure of all the gaseous compounds. That's the one. All right. 103. All right, calculate the root mean square velocity for oxygen molecules in a sample of oxygen gas at 11.8 degrees C. And the R value in this case is the 8.3145, because we need energy this time. Okay, what is the root mean square velocity formula? Right, it should be in your useful information. I might be able to do it. Let me see if I can remember what it is. The root mean square velocity. Let's see. Equals a square root of 3RT over molar mass. I think that's it. Let me see if I got it right. 3RT over. Yep. Okay. It's important though, because R is 8.3145 joules per mole K, and joules is a standard SI unit, which means if you've got anything, if your mass is in here, it's got to be kilograms. Yeah. Oxygen. Well, we normally would calculate oxygen molecular weight as 32 grams per mole. But what we need that is in kilograms. So we got to convert this grams to kilograms, right? They're 10 to the third grams in a kilogram, which means 32.00 times 10 to the minus 3, because it came from the denominator to the numerator. Or we can say 3.200 times 10 to the minus 2 kilograms per mole. Okay, so that's what would go right in here. Did they give us a temperature? Yeah, 11.8 degrees Celsius. So 11.8 degrees C plus 273 equals, let's see, 284.8 K. That's it. We can calculate it now. So the velocity equals square root of 3 times 8.3145 times temperature, 284.8, divided by 3.200 times 10 to the minus 2 kilograms per mole. Now let's see what we get. 3 times 8.3145 and 284.8 times that, and then divided by 3.2 exponent negative 2. And then take the square root. So as an intermediate step, I get 2.21997 times 10 to the 5th. And the square root of that is, I'm going to give it standard notation. Yeah, they've got standard notation. 471 meters per second. Let's see. 4. Oh, okay. So yeah, we can have 4 significant figures. That's right. Meters per second. So if you do it with SI units, the SI units for velocity are meters per second, because meters is standard length and seconds the standard time. All right. That was 103. How are we doing? 109? 109. Which of the following is included as a postulate in the kinetic molecular theory of an ideal gas? Okay, well, let's see. What does A say? The distance between gas molecules is small compared with the size of the molecule. No, the distance is huge compared to the size of the molecule. That one's not A. All collisions between molecules are elastic. Yes, that one's true. There's a total conservation of kinetic energy with each collision. C, in an average collision between molecules, both molecules have the same kinetic energy. No, not necessarily. Now, at a given temperature, all the molecules together are a root mean square average kinetic energy, but they're not all the same. They're a distribution. So C is false. Well, actually, we found our answer already, right? B is the answer. C, well, D, all molecules move randomly in zigzag directions. Well, they do move randomly, but zigzag implies that we know what they're doing, but we don't. They just move randomly, period. All molecules have the same velocity. Nope, sorry. They have the same kinetic energy. But if the molecules are different masses, that means that the smaller ones will be moving faster than the heavier ones. So they don't have the same velocity. Okay, so B is the only one that works. (109) 111, Graham's law. All right, remember Graham's law? Let me see if I can find it in useful information. It relates the molecular weights to the rate of diffusion, or the distance traveled, actually, is the way it's most often expressed. Diffusion rate, or in your useful information, it's written this way: fusion rate of molecule A ratio to a fusion rate of molecule B is equal to the square root of the molar mass of B divided by the molar mass of A. Okay, so this, since it's written as rate, which is true, the rate ratioed is the square root of the inverse rate for the molecular weights. But if you have the fusion rate ratio, can also be the distance ratio. Okay, that works also. So let's see which one fits. Let's see. Equal amounts, volume. We're looking for effusion rates. E. The rates of effusion of gases are inversely proportional to the square roots of their molar masses. That's what that says in English. All right, let's see if we got any more. Could be getting close. Nope, got another one. 116. Okay, hydrogen and chlorine gases react to form HCl. Hydrogen gas and chlorine gas react to form hydrogen chloride gas. So let's balance it. Just like that. You and a friend are on opposite sides of a long hallway. You with hydrogen and your friend with chlorine. You both want to form HCl at the middle of the room. So which of the following is true? All right, let's say like this, we have a long room. And my friend and I are at opposite ends. And let's say this friend has hydrogen to be released. And I have, steak. I have chlorine gas to be released. Okay. Which one is going to move the fastest? Hydrogen is going to move the fastest. So who needs to release first? If you want the reaction to take place in the middle of the room, right here, then you don't want to release this one first because it's going to get there ahead of the chlorine. In fact, it's going to move all the way down here when the chlorine comes. Why? Because these two hydrogens are 2.02 grams per mole. And the chlorine is 70.45 is 90 grams per mole. A lot heavier. So we want to release this one first. Give it time to get part of the way there. Then we release this one and it speeds up and they meet in the middle. Okay, so let's see which one of these answers that question. You should release the hydrogen first. Wrong. Your friend should release the chloride first. I mean, the chlorine gas first. Yes, that's true. Let's see, do we have any oddballs in here? You both should release the gas at the same time? No. D, you need to know the length of the room to answer this question. No, you don't, because it's a ratio, right? It'll have, you could answer the question in any size room. And you need to know the temperature to answer this question. Is temperature mentioned anywhere in Graham's law? No, it's not. Diffusion rate, molar mass, that's it. Temperature is irrelevant. Okay, so B is the answer. Let's see. 117 and 118. We're still talking about the rates of diffusion. All right. Order the following in increasing rate of diffusion. That is increasing rate, that is faster and faster and faster from left to right. Okay. So what does that mean? That means that the fastest one is going to be on the far right, which means the smallest molar mass is going to be on the right. So let's see, we have F2, we have chlorine, we have NO, we have NO2, and we have methane. So let's see, I should be able to estimate and be really close. This one's about 38, right, grams per mole. 19 plus 19. Chlorine we just did. That's about 70 and a half, right? NO is 14 plus 16. That's 30. NO2, that's 14 plus 32. So that's 46. And methane is 12 plus 4 is 16. Right? So they're sufficiently far apart that we don't need to go down to decimals to answer the question. Okay, which one's going to move the fastest? That one right there. Right? From what? Increasing rate of diffusion. So this is going to be the fastest. Right? That's going to be the fastest one. What's the slowest one? This one. Right? Who's left? Well, the next fastest is going to be this one, And the next fastest from that one is going to be F2. And then what's left over? NO2. Okay. So it should be chlorine, right? A or B. Next one is NO2, F2, NO, CH4. A is the answer. Okay. That's how you solve that problem. All right, 118. Complete the following. Because real gas particles have attraction for one another, Okay, right? That's one of the postulates of an ideal gas. In other words, they have no attraction for one another. Their collisions are completely elastic and they behave like billiard balls. But because real gases do have attraction for one another, real gases act most ideally at STP. Standard temperature and pressure, right? Well, they do act ideally at STP, but is that the best answer, right? So let's say A is a possibility. How about B? We assume gas particles have negligible zero volume. That has nothing to do with their attraction, right? Zero volume has nothing to do with attraction. How about C? 1 mole of an ideal gas at STP has a volume of 22.4 liters. Well, it's true, but it has nothing to do with attraction. Okay, so that's false too. Real gases act more ideally at higher temperatures and lower pressures. That is definitely true. E, at least 2 of the above statements, A through D, correctly complete the statement. I guess you could argue for A. Standard temperature and pressure is technically high temperature and low pressure. Right? So A or D could work. D is the best answer. Let me put it to you that way. But if you answer if there's a question like this and you answer at least 2 of the above, A, and you tell me, you point them out, you say, all right, A and D both fit the bill, then I might be inclined to give you credit. All right, 124. Let's see. Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? All right, what we want is a gas that has minimal attraction for its neighbor. Okay. All right, so here are our selections. Remember what we said about attraction. What we want is a molecule that's not polar. Polar molecules tend to have attractions for one another. So if we look at NH3, right, it's going to be like this, right? This, like that, like that. It's definitely polar in that direction, right? So it can't be ammonia. Definitely not ammonia. But the others, let's see, O2, and not enough information to determine. I think we got enough information. Cl2 and H2. What you want is first non-polarity, right? All of these are non-polar, right? Oxygen is like this. Chlorine is like this. That's non-polar, right? There's no differential attraction of electrons either direction. And hydrogen is like this. Okay, so those 3 are all non-polar. But what determines whether or not their attraction, if any, is overcome by environmental conditions? Remember, high temperature, low pressure. If you have the same number of molecules in your sample, right, the pressure is going to be the same. So we can't use pressure. What we need is another factor. If they're at the same temperature, then which one's going to be moving faster? hydrogen's going to be moving faster. And the faster the molecule moves, the shorter the time during impact for the attraction to take effect, if any. Right? So for that reason, hydrogen would be the best selection here. A topic we haven't covered yet is for larger and larger molecules, there's a force that sets itself up because these electrons are in constant motion. And from time to time, they're going to be unequally distributed, which would give you a slightly positive or negative side, which would develop some small amount of polarity. So the bigger ones are going to have a higher attraction for one another. Right? This is the biggest one, then this one, and this is the smallest one. So the smallest one is going to have the least likelihood of developing an unbalanced, even though very temporary, an unbalanced distribution of electric charge. For that reason, plus the velocity is going to be very high. Hydrogen would be the best. Oops. Let's see, did I skip one? No, I didn't skip it. It just froze on me for a second. Okay. All right, 132. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. What's a manometer? A manometer is a barometer that's been modified to measure the pressure inside a vessel containing a trapped gas. Let's go back to the question. Let's see, a manometer attached to a sample of gas that occupies a volume of 2.34 liters. So the volume here equals 2.34 liters. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr lower than. Okay. So it's a different modification. Let me redraw the picture. So here's our gas. That. There we go. So it's kind of like Boyle's J-tube. Only now we have this cylinder attached to it with a volume of 2.34 liters. We don't need this drawing anymore. All right. The mercury level in the arm of the manometer attached to the gas sample on this side is 24.3 torr lower than that of the arm open to the atmosphere. So it's going to be over here like this, and over here like this. So the difference here is 24.3 torr. This one's lower than that one by this amount, which is that many millimeters of mercury. Atmospheric pressure is measured at 1.23 atmospheres. So atmospheric pressure is 1.23 atmospheres. So what's the total pressure here? What's the pressure of the sample of gas? It's got to be enough to support this much mercury plus that much atmospheric pressure. So what we need is 1.23 atmospheres converted to torr. Correct? Yeah, because our answer is in torr. 1 atmosphere is 760. So it's 1.23 times 760. 935. That's what's bearing down here, but we've also got this that has to be supported. 24.3. And let's see, this is 4.8. Let me just do that. It's 4.8. Add those together. Well, let's see, 24.3 plus 959.1 torr. rounded off, 959 torr. That's the pressure on the inside of that vessel right here. And the volume was irrelevant, right? Volume in this case is blue smoke. They're just blowing in your face to try to confuse you. You don't need the volume. All right. We'll sneak another one in here. Nope, we're done.